Deep below the surface, tectonic plates lock together, building massive strain energy. When the rock reaches capacity, the fault ruptures, firing seismic waves through bedrock. It is a common misconception that earthquakes destroy buildings by battering them from the outside. The destruction actually comes from within. The building's own mass fights the movement of the ground. This creates the inertia paradox. Because the base of a building is physically anchored to the earth, it moves immediately with the seismic wave. The roof, however, is suspended in the air. Its mass attempts to stay at rest. The vertical columns connecting the moving base to the stationary roof are forced to bend. As they deform, they generate internal stiffness forces, mechanical tension attempting to snap the column back to its original vertical alignment. Opposing poles from the base and roof focus shear stress directly on the connections, spiking kinetic energy at the beam column joints. Increase the upper floor mass and inertia multiplies. These joints absorb the energy until they exceed their material limits and snap. A structure built to be perfectly rigid will inevitably tear itself apart. Surviving an earthquake requires the calculated management of dynamic kinetic energy. The solution is deliberate flexibility. Most conventional structures are engineered strictly to handle vertical gravity loads, pushing their weights straight down. They lack the continuous load transfer path required to safely route horizontal seismic energy into the foundation. Without horizontal routing, lateral energy exposes the weakest structural links. In traditional construction, these are brittle masonry infill walls and thin, unenforced concrete columns. Stiffness forces from the roof's inertia easily overpowered this rigid four-story block. The lateral movement sheared the concrete supports and blew out the brick infill. This causes a soft-story collapse. The rigid upper floors remain intact, but the unsupported ground floor buckles, dropping thousands of tons of concrete straight down. This happens because seismic waves shake the ground violently back and forth along the X, Y, and Z axes. This creates rapid, reversible deformations in the columns, a back-and-forth whipping motion that brittle materials simply cannot absorb. Even reinforced superstructures face indirect hazards. Violent shaking triggers soil liquefaction and landslides, destroying the earth beneath the foundation and rendering the structural frame useless. When a building is subjected to sudden, multi-directional kinetic force, stiffness guarantees failure. Without the physical capacity to deform safely, the structure collapses catastrophically. Modern seismic design relies on a concept known as the structural fuse. Engineers accept that violent shaking will cause damage. The engineering challenge is dictating exactly where and how that damage occurs. Think of the electrical panel in a house. A fuse sacrifices itself during a power surge to protect the expensive wiring in the walls. In a high-rise, specific joints are engineered to fail safely, sacrificing themselves to keep the main load-bearing skeleton standing. This controlled failure requires meticulous detailing where beams meet columns. These junctions are packed with dense cages of internal steel rebar, spaced tightly together. When the building bends and the concrete cracks internally, these steel rings physically confine the rubble, maintaining its vertical strength. These heavily reinforced joints form a moment-resisting frame. By keeping the connection points rigid while allowing the columns and beams between them to bend, the building flexes cohesively with the lateral load. For structures exceeding 8 stories, steel columns are strongly preferred over concrete. Steel possesses high natural ductility, making it far superior at managing massive sway forces. This critical material property, ductility, the ability to stretch and deform significantly without rupturing, dictates the survival of the building. It prevents sudden collapse and preserves the life of the occupants inside. While the internal skeleton manages forces inside the structure, macroscopic mechanical systems intercept kinetic energy before it even enters the building. The most direct intervention is base isolation. Engineers lift the building's foundation and rest it on top of flexible pads, physically decoupling the structure from the shifting earth below. During a seismic event, the ground beneath the pad moves violently, but the isolator, often a composite of steel, rubber, and lead, shears horizontally. It absorbs the lateral vibration, allowing the vertical column resting on top to remain steady. Base isolation stops energy from entering. Damping mitigates the energy that makes it inside. These devices act like heavy-duty shock absorbers, mechanically slowing down the building's vibrations. Viscous dampers are installed diagonally between beams and columns. When the frame vibrates, a piston forces its way through a cylinder of thick silicone oil. The massive mechanical resistance converts the destructive kinetic energy directly into harmless heat. In super tall skyscrapers, engineers deploy pendulum dampers. A massive steel weight is suspended near the roof. As the building sways one way, the pendulum's inertia carries it in the opposite direction, physically pulling the tower back to its center of gravity. Researchers are now testing a concept called the seismic invisibility cloak. By burying dozens of concentric plastic and concrete rings deep beneath the foundation, incoming seismic waves are forced outward, safely rerouting the energy around the structure entirely. Through isolation and damping, the modern skyscraper operates as a highly tuned dynamic machine, built to actively absorb, dissipate, and counter tectonic force. To maximize this dynamic response, engineers are redesigning the materials themselves. Slurry-infiltrated matte concrete, or SIMCON, bridges the gap between the compressive strength of concrete and the ductile flexibility of steel. Instead of pouring concrete around individual steel bars, SIMCON is injected into pre-packed continuous mats of stainless steel fibers. This extremely high fiber volume gives the material an ultimate strain capacity of up to 0.7%. When SIMCON is pushed past its limit, it fails safely. The continuous fiber mat holds the matrix together, preventing the concrete from splitting into massive, deadly chunks. It crumbles into small, lightweight flakes. Engineering this precise balance of rigidity and flexibility seems like a modern laboratory breakthrough. However, the core physics were mastered centuries ago by traditional builders using local timber and mud. Observe the Daji Dewari architecture of Kashmir. These structures survived the massive 1885 Srinagar earthquake by integrating rigid mud brick masonry inside a matrix of load-bearing wooden piers. The masonry provided the stiffness to handle vertical gravity, while the wooden beams acted exactly like the steel ties in modern concrete. They imparted tensile flexibility, tying the walls and floors firmly together so the entire house swayed as a single cohesive unit. The pharaohs of the Uttarkashi district rely on a similar strategy. They employed timber-cornered rebel masonry, driving vertical wooden columns down through the stone to securely pin the inner and outer layers of the walls together. These traditional homes survived epicenters that easily level solid stone palaces. They survived because they didn't stubbornly resist the lateral loads of an earthquake. They moved with them. Whether injecting cement into stainless steel fiber mats or binding mud bricks with local timber, the physical mandate is identical. Modern engineering is scaling up the exact physics of flexibility utilized in ancient vernacular architecture. When the shaking stops, the city still needs to function. The focus of structural engineering extends past immediate life safety, directly into economic continuity. A major seismic event in Southern California could inflict over $113 billion in direct property damage. That figure excludes the massive secondary losses caused by broken supply chains and business interruption. The vulnerability of major economic hubs remains severe. In Los Angeles, estimates show up to 90%. Resilient design ensures a commercial facility can physically open its doors the morning after a disaster. The financial stakes of ignoring these realities are absolute. In 1971, the Sylmar earthquake struck California, heavily damaging the Anheuser-Busch brewery in Van Nuys. The physical damage quickly compounded into financial losses. The facility was forced to halt operations entirely. During the long reconstruction period, competitors aggressively absorbed their local market share. Recognizing the extreme financial liability of their old structural system, the brewery rebuilt utilizing rigorous new seismic standards, applying the principles of ductility and base isolation. During subsequent major earthquakes in California, the results were definitively clear. The unreinforced rigid structures in the area sustained severe joint failure. The retrofitted brewery, equipped with ductile connections and active dampers, safely dissipated the kinetic loads. The structural upgrade protected their facility and their revenue stream. Retrofitting proved to be a highly calculated business investment that preserved their capital assets and kept operations running. Earthquakes cannot be prevented, and their kinetic energy cannot be outmuscled. True resilience belongs to the structures and the societies that have the engineering foresight to bend without breaking.